All right, so we should be finishing off Unit 2.5, the periodic table notes for this unit here, and covering more and more trends, such as the alkali earth metals. They have a little bit higher density than the alkali metals. The alkali earth metals are group 2 elements. Their ionization energies are low, but they are not as low as, say, those group 1 alkali metals. And that's because their atomic radius is just a little bit smaller. Okay? Not the smallest, just a little bit smaller. Again, no need to copy down this whole chart. You should be able to find it inside the book for this class. When it comes to reacting with water, not all of the group 2 elements react the same. Just as you would guess from looking at group 1 elements, they didn't all react the same either. Beryllium does not actually react with water. Magnesium needs to have steam, meaning it needs something with a little bit more higher temperature. The other ones, the calcium and the barium, will react. It's just kind of late. It does bubble and fizz, but it's not as cool, say, as some of the other group 1 elements. Calcium just bubbles and fizzes, whereas potassium, which is one atom to the left, is much more violent. Barium and strontium do chemically react, but again, it's just a more vigorous bubbling and fizzing, very similar to that what you would see on the picture right here. The reactivity also increases as you go down the group, just like group 1. For metals, that's what you're going to see normally happening. For metals, the reactivity increases as you go down because the atomic radius gets bigger as you go down. As the atomic radius gets bigger, the ease of losing those electrons goes up. That's the ionization energy goes down. Okay? So those things do happen. Now jumping all the way over to the nonmetals. Why jump all the way over to the nonmetals? Because the transition metals have some uniqueness to them that they don't like to follow the nice basic trends that we would normally see in our parts. And so we normally don't see that in the normal groups, so we kind of skip over them altogether. Oxygen, sulfur, selenium are considered nonmetals. Tellurium is a metalloid, and polonium is the metal. So their likelihood of looking like a metal increases as you go down the periodic table. Some of the other things about the nonmetals, such as nitrogen and oxygen, these groups do have names. They are not very commonly referred to them, these groups by their name. So a lot of times we don't mention them by that. And so it is usually looked at as just group 16 for this case, for sulfur and selenium being the only non-metals in there. Oxygen is also a gas, where sulfur is not a gas. It is actually a solid, usually found as very similar to that of a yellow powder. Usually does have an odor that a lot of people associate with sulfur and sulfur pits, say if you went to one of those locations. Sulfur is a weaker oxidizer. Okay, It will oxidize things, but is not as abundant to oxidize. Although it does also form what's called an allotrope. Allotropes mean that it's the same thing. And so you would have like sulfur, just S, and S8 are allotropes of each other. It's the same thing, they just have a different structure, so to speak. There are others. Oxygen has an allotrope as well. Oxygen normally diatomic as we breathe it is O2. Ozone is O3. These are considered allotropes. It's still the same thing, oxygen. They come to form a different molecule. And because they have a different molecule and they also have different chemical and physical properties. I like to breathe oxygen at this level of the atmosphere. I do not want to breathe ozone at this level of the atmosphere. At upper levels of the atmosphere, I want ozone to be there because it protects me from UV light, where oxygen at those upper levels doesn't as much. And so therefore, they have different properties, both chemically and physically, and that's kind of an important thing. See if you were paying attention earlier. A soft gray solid reacts with water to form a flammable gas and is a basic solution. Not simple, just basic. The solid most likely is, the next group would be the halogens, sometimes also referred to as the halides. Sometimes referred to as the halides. They're your prototypical nonmetals, meaning they're highly reactive. They do, as you would guess, react very commonly and frequently with the metals. They have a difference in how they chemically react. They chemically react a little bit backwards. Their reactivity actually increases as you go up the periodic table. Their reactivity increases as you go up the periodic table. So that's a little bit different than what we have been working with. A lot of the ones with metals, their reactivity increases as you go down. Well, with the halides or the halogens, their reactivity increases as you go up. So the most reactive non-metal would be fluorine as we look at this group, where iodine would be the least reactive. Now it should, and there is actually a connection between which one is which and the why. And it comes down to the fact that these are going to be, you go from a gas at the top, and then chlorine is also a gas, but then you go to a liquid, then you go to a solid. So as you go down, their reactivity decreases, and what they look like also changes. Remember, all of the group 7s are also diatomic, meaning when we see them in their natural form, we see them as a pair. So when we see them in nature, we see them as a pair. Meaning two, not the fruit. Bracha. These group 7, as we kind of mentioned before, they all tend to have very large electronegativity, or electron affinities are very negative, meaning that they form those positives and negatives, or they tend to react with a positives and highly form that negative anion that we will really talk about in much more great length in chemical reactions and especially chemical names. These are very commonly found in a lot of compounds. That's why they're salts. And when we say salt, a lot of times people think of sodium chloride, which in some ways is correct. Sodium chloride is a salt. However, it is not a salt that we would all talk about. And in chemistry, all salts are solid ionic compounds. With that, and so anything that is a solid ionic compound, that's what that would be. They each have their own little part, and say you would have chlorine is added to the water supply for disinfecting purposes. Iodine, a lot of times people think what you get put on you at the hospital is iodine. It's actually called beta iodine. That's why it doesn't have that brown look on it when we're looking at it on the screen there. The bromine is more of a brown color, where iodine is actually a purple. And the last group that we talk about for their trends is the noble gases. They have astronomically high ionization energies. Why? Because they have an octet. They have all the electrons that they want. And therefore, they do not want to lose any electrons. They also have electron affinities that are positive and therefore are pretty much unreactive. Hence the name noble gases. Noble meaning non-reactive, and therefore they are also considered to be monoatomic, meaning they only form with themselves, which they don't. When they are found in nature, they are found as a argon atom. Now, it has happened in more recent history that these noble gases do chemically react, but it takes a lot of heat and pressure for that to happen. It is not something that happens quickly and easily. A lot of heat and pressure are required to get these elements to chemically react. And if I'm not mistaken, neon and helium have yet to chemically react. I believe argon has reacted under very, again, extreme conditions. Argon is actually the third most abundant gas in our atmosphere. Nitrogen being 1, oxygen being 2, and argon makes up 0.9% of our atmosphere. we're actually running close to a helium shortage based on the fact that it does easily leave our atmosphere. So for this question, noble gases are what? Noble gases are monoatomic. The other answers on the screen, for the most part, again, they're generally unreactive, but it's the B that is the incorrect, is that they do not have the P subshells, and therefore all of the above is also an incorrect answer. So the only correct answer is monoatomic. And that concludes notes for Unit 2.5.